Good morning, champs. Today we build the mathematical toolkit of advanced fluid mechanics. Everything that follows, creeping Stokes flow, vortex motion, potential flow, relies on a precise understanding of a few differential operators. The coordinate system may change, but the physics does not. We begin with the nabla operator. In Cartesian coordinates, nabla consists of partial derivatives with respect to x, y, and z. In cylindrical coordinates, it includes derivatives in the radial, circumferential, and axial directions with the appropriate geometric factors. In spherical coordinates, it includes radial and angular derivatives scaled by r and sine theta. The form changes with geometry, not with physics. Now the gradient. The gradient of a scalar field is nabla applied to that scalar. In Cartesian coordinates, let pressure equal P0 plus 2x minus 3y plus 5z. Differentiate with respect to x to get 2, with respect to y to get minus 3, with respect to z to get 5. The gradient is the vector 2, minus 3, 5. In the momentum equation, minus the gradient of pressure is the pressure force per unit volume. Pressure pushes fluid toward lower pressure. In cylindrical coordinates, let pressure equal P0 minus A times Z. The derivatives with respect to r and theta are 0. The derivative with respect to z is minus a. The gradient is purely axial. This represents a constant driving pressure gradient in pipe flow. In spherical coordinates, let phi equal a divided by r. The derivative with respect to r is minus a over r squared. Angular derivatives vanish. The gradient is radial and decays as 1 over r squared. In potential flow, velocity equals the gradient of a scalar potential, giving a purely radial field. Next, divergence. Divergence measures local expansion or compression. In Cartesian coordinates, let velocity equal 2x in x minus y in y and 3z in z. Differentiate 2 from the first term, minus 1 from the second, plus 3 from the third. The divergence is 4. Since it is not 0, the flow is not incompressible. In cylindrical coordinates, consider fully developed pipe flow with only axial velocity depending on r. The radial and circumferential components are 0, and axial velocity has no z dependence. All divergence terms vanish. The flow satisfies incompressibility. Now curl, also called vorticity. Curl measures local rotation. In Cartesian coordinates, let velocity equal minus omega y in x and plus omega x in y. Compute the derivatives carefully. The only non-zero contribution produces 2 omega in the z direction. Rigid body rotation has vorticity equal to twice the angular velocity. In cylindrical coordinates, consider swirling flow with circumferential velocity depending on r. The axial vorticity equals 1 over r times the derivative of r times that velocity. For solid body rotation, velocity equals omega r. The result is 2 omega. For a free vortex, velocity equals circulation divided by 2 pi r. The derivative vanishes, so the flow is irrotational outside the core. In spherical coordinates, if velocity equals the gradient of a scalar potential, such as a over r, the curl is 0. Potential flows are irrotational. Finally, the Laplacian. The Laplacian of a scalar is the divergence of its gradient. In Cartesian coordinates, take phi equal x squared plus y squared plus z squared. The second derivatives are 2, 2, and 2. The Laplacian equals 6. In cylindrical coordinates, let phi equal r squared. Differentiate once to get 2r. Multiply by r to get 2r squared. Differentiate again and divide by r. The result is 4. In spherical coordinates, let phi equal 1 over r. Differentiate to get minus 1 over r squared. Multiply by r squared and differentiate again. The result is 0 for r not equal to 0. This is Laplace's equation, fundamental in potential flow. These operators, gradient, divergence, curl, and Laplacian, form the foundation of the governing equations. In the next videos, we will derive continuity and momentum equations from them. Then we will apply them to creeping flow, vortex flows, and potential flow in detail. Master these tools, and the structure of fluid mechanics becomes clear and systematic.